All right, so in the last video, we looked at how to evaluate the 6 trig functions at some very particular angles, namely at all the multiples of pi over 2, so 0, pi over 2, pi, 3 pi over 2, and 2 pi, and then the 3 other standard angles in the first quadrant, namely pi over 6, pi over 4, and pi over 3. And then also, we know that if you go around the circle clockwise to get negative pi over 2, negative pi, so on and so forth, we land at the same terminal side, and so we have the same sines, cosines, and so on and so forth. What we want to do now is extend the ability to compute those trig functions at angles in the second, third, and fourth quadrants, right? And so to that end, we're going to define something called a reference angle, right? And we're going to make use of the symmetry of the circle in that sense. All right, so by definition, you can measure these angles in degrees or radians, right? Whatever one is more comfortable for you at the moment is fine. The reason we need radians is going to become apparent when we try to graph these as functions of x in the xy plane, right? So we need to be dealing with inputs that are real numbers and not circular measurements, all right? So that's the whole point of that. But we define them the same way, namely, if you give me an angle between 0 and 360 degrees, and it's not a multiple of 90 or 180, right? So it's an angle strictly, if you look at the radius, it's strictly in the first, second, third, or fourth quadrants, not on one of the axes. Then the reference angle, you take your angle and you subtract it from 0 and from 180, right? Take the absolute value of that difference to make sure it's positive. And the smaller of those 2-degree measures is defined to be the reference angle. And if you want to do it in radians, then we know that 180 degrees is equivalent to pi radians. So you do the same thing, but you replace the 180 by pi. All right, so let's actually see here. So let's look at a couple examples. 135 degrees, if you were to sweep out that angle on the unit circle, you'd have the radial segment ending up here, right? So it ends up in the second quadrant. You want the reference angle, you're going to subtract your 135 from both 0 and 180 and take the absolute value, right? So if you do that, 180 minus that guy is 45 degrees, whereas the other one is just itself, it's 135 degrees. The smaller of those two is 45 degrees, and so that's what the reference angle is. Doing this, the reference angle is always going to be in the first quadrant, right? And so the nice thing there is that we know that in the first quadrant, we have 3 very particular angles that we know how to compute the trig functions of, right? That's what we did in the last section. And so that'll be helpful here when we try to compute the trig functions of multiples of those angles in the other quadrants. All right, and then for this guy, if you subtract 7 pi over 6 or from pi and from 0, you get pi over 6 in itself. So pi over 6 would be the reference angle in this case. Right, pretty cut and dry. All right, so this is just a kind of a reference. If you didn't want to do that every time, if you just want to picture it, this is a way of getting the reference angle itself in the other quadrants, right? But all you really need to be able to do is the definition there. All right, so in terms of your turn, here, I'll just stop there. Since I already showed it, I might as well talk about it, I guess. So for 330, you subtract it from 180 and from, oh, I see. So up here, remember, hold on one second. Okay, back at it, sorry about that. All right, so now for the 330, it's a little bit different in this case. If you were to subtract 0 and 180 from that, you'll get numbers both of which are larger than an angle that's in the first quadrant. And so here, what you can do, if you notice, 330 degrees would be in the fourth quadrant. It's right around here. And so technically, it's closer to 360 than it would be to 0, right? So remember, 0 and 360 degrees have the same exact terminal side. And so in this case, if you're in the fourth quadrant, subtract your angle from 360. Right, that's equivalent to subtracting it from 0, so to speak, and then you'll get your angle of 30 degrees. Right, you always want that angle so that it's in the first quadrant. Right, so anytime you're in the fourth quadrant here, subtract your angle minus 360, take the absolute value, and then that'll give you the reference angle. For 5 pi over 4, if you subtract either 0 or pi from it, the numbers you get are itself and pi over 4, so pi over 4 is the reference angle. Okay, now how do we exploit this idea with the symmetry of the circle? All right, so let's take a look at this picture here. All right, so notice here that I'm just going to label a point in the first quadrant on the circle. Let's call it xy. We know that the circle is symmetric with respect to both the y and the x axes, right? And so what that means is if I take this point and I reflect over the y axis, I'm going to get this point here. But by the very nature of the reflection, the angle that was theta here has to be the angle theta there, right? Because this whole triangle is being preserved by reflection. All right. Notice that the relationship between these points is simply that the sign of the x-coordinate has changed, right? It's the same distance from the origin, but on the opposite side. And the y value hasn't changed at all. It's still just y. Likewise, if you take this point and reflect over the x-axis, the x stays the same, but the sign of the y-coordinate changes. And then vice versa here, if you reflect either this point or this point over the x or y-axis respectively, you get the same distances from the origin, but now both signs are opposite what they were back in the first quadrant. So how do we use that, for instance? Well, what if I took the point that corresponded to pi over 4? Remember in what we did in the last section, that point had the same x and y because it was on the 45-degree line, and those coordinates were 1 over root 2, comma 1 over root 2. So if I were to take that point and reflect it over the y-axis, I get the point negative 1 over root 2, comma 1 over root 2. Okay, so we have a point on the circle, but linked to that point is the angle it makes with respect to the positive x-axis, right? So if I start here, I went up pi over 4. This angle's pi over 4, right? And so the angle between here has to be pi over 2 because these three angles form a straight angle, right? Pi over 4 plus pi over 4 is pi over 2. So this has to be pi over 2. You'll say, well, so what? Well, that means that if I went from the x-axis to that terminal side over here, I'm really sweeping out the angle pi over 4 plus pi over 2. That's 3 pi over 4, right? So we have a new multiple of pi over 4 that we know the point on the unit circle, namely at 3 pi over 4, that angle, the point on the circle is negative 1 over root 2, comma 1 over root 2. But remember, the x-coordinate of a point on the circle is the cosine of the angle that's used to get it. So that means the cosine of 3 pi over 4 has to be minus 1 over root 2. And likewise, the sine of 3 pi over 4 has to be 1 over root 2. All right, so we exploited the symmetry with the idea of the reference angle to get that point, and so we know the sine and cosine of yet another angle. Same sort of thing down here. If I reflect this guy over the x-axis, that's another angle theta, that's an angle theta. So from beginning to end, if I went from the positive x-axis, this whole thing here is pi plus pi over 4, that angle is 5 pi over 4. But I know that the point on the circle that corresponds to it is negative 1 over root 2, 1 over root 2, or negative, I'm sorry, they're both negative. And so both the cosine and the sine of 5 pi over 4 are negative 1 over root 2. Right? And then finally here, if you go to this side here, I'm adding another pi over 2 to 5 pi over 4. So the angle that I sweep out is 7 pi over 4. I know that the coordinates of the point of the circle that match up to that point are the same as these with the negative y, right? So it's 1 over root 2, comma negative 1 over root 2. So I know the cosine of 7 pi over 4 is 1 over root 2. The sine is negative 1 over root 2, right? Now I could play that game for both the other multiples of pi over 3 and pi over 6 in the first quadrant, right? Again, by symmetry. All right, and so that's what yields this big circle here, right? You're like, oh no. But this is the typical sort of unit circle. You don't really need to memorize this. What you really need to do is know these values here and understand how to get them, right? Over time, the more you use it, the more this will stick. But to memorize the whole circle is kind of pointless if you know that to get these other angles, you simply change the sign of the correct coordinate of the point, right? But these are all of the ones that will come up frequently, and so you'll need to know them either at your fingertips or be able to compute them quickly. All right. I've already talked you through the example for pi over 4. So I'm going to allow you to, well, actually, I'll do this one, and then I'll let you look at the org turn together. So example 2, we want to evaluate all the trig functions for 2 pi over 3, right? And so using our symmetry, here was pi over 3, right? The point was 1/2 root 3 over 2. And I know that if I reflect that over the y-axis, right, since this is pi over 3, that's pi over 3, well, then this has to be pi over 3, right? They all have to add up to pi. It's a straight angle. So all told, I went pi over 3 plus pi over 3. This does correspond to 2 pi over 3. And we know that the point over here, you simply change the sign of the x coordinate to get that point. And so I know the point corresponding to 2 pi over 3 is -1/2 comma root 3 over 2, right? And so I know exactly how to compute the cosine of the sine. The cosine is -1/2, and the sine, sorry, my dogs are crazy, and the sine is root 3 over 2. And then to compute the tangent, you divide sine by cosine, right? So if you do that, you get the minus radical 3. Secant is 1 over cosine, cosecant is 1 over sine, and cotangent is 1 over tangent, or cosine over sine, right? So you can just use those definitions to compute those. All right. For this your turn, go ahead and try that and then check yourself, but it's the same exact process. You want to find the angle in the correct quadrant that corresponds to a multiple of that angle in the first quadrant. Use the symmetry to get the sine for each of the coordinates, and then just use the definitions of sine, cosine, and the other 4 trig functions to compute. So give those a try, and then I'll scroll up so you can check yourself once you're done. All right, so go ahead and check yourself with these. So there's that guy. You can pause that to check. All right, so 5 pi over 4 is in the 3rd quadrant. 11 pi over 6 is in the 4th. And 4 pi over 3 is in the 3rd. Okay, so now we can take care of the standard angles between 0 and 2 pi. But now what if I gave you an angle that was larger than 360 degrees or 2 pi, right? So how do we deal with those? So let's take a look. Let's think about it. So suppose you went from 0 to 360 degrees, and then I went another 90 degrees. So I went, all told, the amount of turn that I had is 450 degrees, right? But notice that that 450 degrees lands exactly on the unit circle, the same place that 90 degrees did, right? So if that's true, then the sine and cosine of the 450 degrees have to be the same as the sine and the cosine of 90 degrees respectively, right? Remember, because the sine and the cosine of an angle corresponds to the x and the y coordinates of the point of the circle where that thing lands. And so with that said, we know that you're going to keep repeating these values the more you go around 360 degrees. All right. And so here, this is just a formal way of writing it out. But what this says is if your angle is bigger than 360 degrees, then you can rewrite the angle as a certain number of full rotations plus a remainder, right? So suppose, for instance, suppose we went around 720 degrees. That means that you've gone around the circle counterclockwise twice and you have no remainder, right? So you end up with that angle theta equals 720 degrees corresponds to the same angle as 0 did. If I had taken the angle 730 degrees, then you would have gone around twice and then added 10 degrees to that, right? So the remainder, it tells you the angle in the usual circle that particular larger angle corresponds to. So 730 degrees corresponds to the exact same location on the circle as did 10 degrees. Come on in. All right. And you can do the same sort of thing in radians, right? So always what you're going to do to find the terminal side that corresponds to your angle, you're going to find the number of rotations. So you're going to divide a angle in degree measure by 360. The whole part of that is irrelevant. It just tells you the number of times it went around. You're really interested in the remainder because that will tell you the terminal side that you're interested in. If you're looking at radians, then you divide your angle by 2 pi, right? The whole part again is the number of times you went fully around. The remainder is what you want. All right, so let's look at these. So you have sine of 23 pi over 6. Okay, so I'm going to divide 23 pi over 6 by 2 pi. If I do that, I get 1 full rotation plus a remainder of 11 pi over 6. Okay, so that means the terminal side of 23 pi over 6 is the same as 11 pi over 6. And I know how to compute the sine of that, right? 11 pi over 6 is a multiple of pi over 6. So pi over 6 was in the first quadrant, 11 pi over 6 is in the fourth, so you're dropping down over the x-axis. That value becomes negative 1/2. All right. For 52 pi over 3, you do the same thing, only now I'm going to still divide by 2 pi, and it turns out that if you do that, you get a whole part of 8 with a remainder of 4 pi over 3. So I went around 8 full times, right? And then when I stop there, I go another 4 pi over 3. That 4 pi over 3 tells you the terminal side that you're interested in, right? It lands, so 52 pi over 3 lands you at the same place on the circle as did 4 pi over 3. And so their sine and cosines are the same. But if their sines and cosines are the same, their tangent must be, because you use the sine and cosine to define the tangent. If you look at the unit circle, 4 pi over 3 is a multiple of pi over 3 that's in the third quadrant. And so you take the point that corresponds to pi over 3 and make both of those components negative. So the sine is negative root 3 over 2. The cosine is negative 1/2. And so the tangent is the quotient of those two, which is root 3. All right, so practice that. It's not hard, but just practice that to kind of get a feel for how you find these trig functions based on where these terminal sides are. All right, so I'll show you this your turn. Stop the video here and try this, right? Take some time, be careful with it, and then check yourself. All right, so here are the answers to those. So pause that, make sure you check yourself. When I write these things out like that, it's to emphasize an identity that's coming later. But really all I'm doing in here is I'm dividing by 2 pi, and then I'm looking at the number of 2 pi's plus the remainder, and then I'm just taking into account the remainder here. All right, let's look at a couple of identities. So first, hold on one second, let me close the door. Okay, sorry about that. So in terms of identities, right, what we noticed, what I've been talking about is if you look at the number of times you've gone around the circle, right, so we get this multiple of 2 pi, and then you have a remainder. If you take the terminal sides of this angle here and theta are the same, and so they have the same sine and cosine. So in terms of an identity, we have these two that always hold. Give me any theta you want. If you add a multiple of 2 pi to it, and that could be positive or negative, as we'll see in a moment, then you still get the same sine and cosine. Right? So those are called the periodic identities, right? In terms of an angle with a negative measure, you're just going in the opposite direction, right? So all you have to do here is sweep out pi over 6, pi over 4, and pi over 3 in the opposite direction. And what you'll notice when you do that is that the reflection's over the x-axis. And so the only thing that's going to change there is the sign of the y, right? So you can always talk about how terminal sides compare for an angle in its opposite pictorially, right, using the symmetry. All right, so if you look at these, right, so if you take the sine, okay, so go back up here and notice that for each of these pairs, if I took an angle and its opposite, the x coordinates stayed the same, right? So the x coordinates, remember, are the cosine of those angles. So here, the cosines are the same in each of those guys. whereas the sine of the y's became the opposite since we were reflecting over the x-axis. And so notice that in each case, those are the same but in opposite directions. One's positive and one's negative. And so those are called the even-odd identities, right? If I take the sine of negative theta, I get the opposite of what I got for just theta. If I take the cosine of negative theta, I get nothing unchanged. I get the value that's unchanged. It's still the cosine of theta. We call those the even-odd identities because that is exactly how you define an odd function and an even function in general, right? You take, if you apply a function to a negative input and get the same thing as negative of f of the original input, it's odd. And here, if you take f of negative theta and you get f of theta back, as you do here, it's an even function, right? All right, so this will be helpful. This and this, these two identities are going to be helpful in the next section when we try to graph the sine and the cosine functions. All right, and so here is just more practice for you. You're still dividing this by 2 pi, but now the thing you have to be careful of here is you're going in the opposite direction. And so while you're dividing by 2 pi, the remainder that you're going to get is going to be negative. And so you're not going around this way, you're going around the other way. And so you make sure you realize that's because your terminal side is going to land in a different place than it would have if it had been positive. So that's the only new wrinkle there. Just keep it in mind, try these and then check yourselves when I pull up, once you are done with them. All right, so those are the answers here. If you want to pause yourself, just take a look and see, but these are exactly the same approach. And in often cases, what I've done here is I got rid of the negative. So you could handle them one of two ways. You can directly divide by 2 pi like I was hinting, and then take your sine or cosine of the negative value by looking at the terminal side. Or even better, what I opted to do here is directly use the even-odd identities. So here, the cosine of that guy with a negative inside is the same as the cosine without the negative, so I got rid of it. You don't have to worry about the negative. On sine over here, though, I can't just get rid of the negative. I need to actually multiply on the outside by it, right? But in either case, you can remove that negative from the input by using those identities. All right, now a related problem that you're going to bump into is solving what are called trig equations, right? We're going to want to find certain angles for which the sine or the cosine or some other trig function is equal to a prescribed value. Now that said, this is really the same thing that we've been doing, but just asked slightly differently, right? So let's look first at this guy. Let's suppose you want to find all angles theta in radians for which the sine is a half. All right, so if you think about this, what you want to do is find all of the angles that are on the unit circle period, right? So you don't worry about going around 27 times. Just for a single rotation of the circle, you want to think back to your unit circle and think about what theta values that we knew about landed at a point where the y value was 1/2. Right? And if you think about that, you'll notice that since the sine is the y, pi over 6, you can look back, that actually had a sine of 1/2. And then if you reflected it over the y-axis, you got 5 pi over 6. That had a sine of 1/2. Right? So both of these values here, the pi over 6 and the 5 pi over 6, are solutions of that equation. So here, also, if I happen to stay at pi over 6 and go around 2 pi, or 4 pi, or 6 pi, or in the opposite direction by -2 pi, -4 pi, so on and so forth, I get another terminal side for that angle that lands exactly at those angles by the periodic identities. And so technically, if I take pi over 6 and I add or subtract any multiple of 2 pi from it, same for 5 pi over 6, I get another solution, right? So these are the solutions here. Notice I specified that n has to be an integer, right? You can't take any old number, like a half. If you go around only half a circle, you're not going to land at the same point. Right, so just be careful with that. You should specify always here that the n is an integer multiple. All right, and then this guy, same sort of idea. You want to find the angles for which the cosine is -1. So again, start in 0 to 2 pi. Right, what angle do we know of in the standard circle that gives you a cosine of -1 or a value of the point of the circle that has an x of -1? Well, there's only one of those this time. It's exactly at pi. Right, so you go around 180 degrees or pi, That x value is -1, so that is a solution. But now you also add 2n pi to that because you can keep going around the circle as many times as you want and land at that same point, right? And so pi plus 2n pi, or if you yank the pi out, this expression ran as an integer, are all of the solutions of that equation. All right, and then here, same sort of idea. Again, these emulate the examples. You want to find the values of theta for which the sine is equal to 1, and then also the cosine, or the values of theta for which the cosine is √3/2. Emulate what we did in the previous example to see what those solutions would be, and then check yourself. All right, so if you unpaused, these are the solutions of that. Again, the sine of theta is only 1 when theta is pi/2, and so if you add 2n pi to that, you'll get all your solutions. Here, there are two values with an x coordinate of √3/2, namely pi/6 and 11 pi/6 in the fourth quadrant. And so if you add 2n pi to those guys, you get all the solutions. All right, so now we're going to do the same sort of thing, but make it slightly more complicated in the sense that now I'm going to plug in not theta for the input, but let's say 3 theta or 4 theta or whatnot, right? So I still want to find all the angles theta for which these equations hold, but now we have an added wrinkle. All right, so first things first, the initial strategy is the same, right? So that's good, right? Notice here that I want to find all angles, that all angles here is just 3 theta, right? So I want to find the values of 3 theta for which the sine is 1/2, right? What we already did, we already found the angles for which the sine was 1/2 in the earlier exercise, namely pi/6 plus 2n pi and 5 pi/6 plus 2n pi, right? We already looked at that here. The only new wrinkle is, now instead of a theta, I have a 3 theta in here. So these guys here are not my theta values, those are my 3 theta values. Okay, and so what I want to do to find the values of theta that I can clunk in here, I need to divide through both these by 3, right? And so if I do that, I get a kind of this expression here that I simplified. But the key here is you attack these problems by letting the entire input equal the known values that you get, and then you solve those equations for the actual theta value. Here that just requires us to divide by 3. Here you'll do the same thing, right? Remember the cosine of something was -1 when that something was pi plus 2n pi. But that something now is 2 theta, not theta. And so to find the values of theta, I'm going to divide that by 2, right? And so that's what I show you here, right? The values of 2 theta are pi plus 2n pi, but I want theta, so I divide by 2. Okay, that's the only difference. But you have to remember to do that. And you have to remember to include all of the values by adding on that 2n pi. All right, again, another your turn. You're trying to, here again, you solve the equations with just theta in there in the previous your turn. So use those solutions here. And then you want to find the values of theta for which this is true and that is true. So you have to divide by just the right number each time. So go ahead and do that and then make sure you check yourself. All right, so here, you're just going to take your values that worked before and divide by 4. And here you take the values that worked and divide by 5. All right, so it's the same thing we just did. Just be careful of what the input looks like so that you actually get the values of theta and not a multiple of it in the answer. Okay, so there's a lot going on in this section, all related, but a lot of extra work in terms of reference angles and whatnot. So take your time through these problems. They're all fairly standard, but take your time and actually go through just to make sure that this is well cemented in your mind. All right, let me know how it goes.